Hello my friends and welcome back to the You Can Do TV channel. The production of wire rod at Pittini is structured as a continuous, integrated process, beginning with the recycling of ferrous scrap and ending with carefully coiled products ready for downstream industries. In the steelmaking stage, selected scrap is melted in electric arc furnaces, refined in ladle furnaces to achieve a consistent chemical composition, and then cast into billets. These billets, uniform in size and quality, serve as the feed material for the wire rod rolling mill. At the Verona site, one of Europe's most advanced mills is dedicated to this transformation. Billets are reheated to restore ductility before entering the rolling line, where a sequence of roughing, intermediate, and finishing stands progressively reduce the cross-section while ensuring structural integrity. Rolling speeds can exceed 100 meters per second, supported by automated loopers, laser measurement, and quick roll change systems that allow uninterrupted production. Throughout production, data acquisition systems monitor thousands of parameters, enabling precise control of temperature, rolling pressure, and coil weight. This Industry 4.0 integration ensures full traceability, predictive maintenance, and optimization of energy use. After rolling, every coil undergoes inspection for surface quality and dimensional accuracy, with certification issued to confirm compliance with international standards. Future expansion at Verona includes a new finishing line capable of producing bars from 8 to 36 millimeters in diameter, in lengths up to 18 meters, with automated bundling of 5-ton packages, scheduled for completion by 2025. In this way, wire rod emerges as a versatile semi-finished steel product, created through a sequence of controlled metallurgical and mechanical processes, forming the basis for numerous applications in construction, automotive, energy, and mechanical engineering industries. Once the final diameter is achieved, the wire passes on to controlled cooling conveyors, where the cooling rate is adjusted to create the desired microstructure and mechanical performance. The resulting wire rod is then formed into coils, each weighing around 2 tons, secured by automated bundling systems. The dimensional range covers smooth rods from 5.5 to 20 millimeters and ribbed rods from 6 to 16 millimeters. Low carbon grades are produced for drawing, galvanizing, and welding, often alloyed with silicon or boron for improved ductility and finish. Medium carbon grades, such as G3V42 to G3V66, are suitable for fasteners, tire reinforcement, and mechanical parts, balancing strength with workability. High carbon grades, ranging up to G3V82, reach tensile strengths of over 1200 megapascals and are employed in demanding applications like pre-stressed concrete, springs, and steel cord. Forge Masters International in Sheffield operates at the forefront of heavy steel production, combining advanced machinery with precise engineering processes. The facility's heavy machine shop can lift components up to 500 tons and handle castings of 600 to 650 tons of molten steel, producing finished parts weighing up to 350 tons. These massive operations require meticulous planning and coordination of lifting systems, furnaces, and machining equipment to ensure accuracy and safety. The steel is poured into large molds, where controlled cooling and solidification processes determine microstructure and mechanical properties. Once cast, components are moved to precision machining centers for milling, drilling, and surface finishing, achieving tight tolerances critical for high-performance applications. Hydraulic presses, CNC-controlled lathes, and multi-axis machining centers are all integrated into the workflow, reducing manual handling and improving consistency. Forge Masters focuses on sectors requiring extreme reliability: offshore platforms, nuclear and power generation turbines, and defense components. Stainless steel derivatives and specialty alloys are processed with precise temperature control, stress relieving, and heat treatment cycles to achieve the required hardness, corrosion resistance, and dimensional stability. Automation and monitoring systems track casting temperature, machining alignment, and dimensional measurements in real time, ensuring each component meets rigorous technical specifications. Despite the enormous scale of operations, around 800 skilled workers manage peak production of 100,000 tons per year, demonstrating how advanced infrastructure and technology optimize productivity while minimizing labor. Forge Masters exemplifies modern steelmaking, combining historical expertise, engineering precision, and advanced machinery to deliver components that meet the highest standards of safety, strength, and durability in critical industrial applications. Leas. In modern hydropower engineering, turbine manufacturing at Vasrafolk WKV represents a precise and controlled process. Every structural element is produced in dedicated steel workshops, where accuracy begins with fabrication and continues through advanced machining centers. These facilities allow components to be shaped with exact tolerances, ensuring long service life under demanding operating conditions. Research findings from WKV's laboratory feed directly into design improvements, keeping turbines aligned with the latest technological standards. Final assembly brings together the hydraulic turbine and its integrated control and monitoring systems. Each unit undergoes thorough functional testing, where efficiency, load response, and safety mechanisms are carefully verified. Once pre-assembled and packaged, the turbines are transported to the installation site, ready for commissioning. The result is a fully engineered system built for reliable and efficient hydropower production. How does a flat steel plate become a towering structure that supports massive wind turbines? The manufacturing of wind turbine towers at Katana Summit follows a precise sequence of heavy fabrication and quality control. Production begins with raw plate steel, sourced from domestic mills in grades specified by turbine manufacturers. Each plate is cut to dimension on a plasma cutting table, with edges prepared for welding. To ensure clean surfaces, plates pass through a wheel abrader before rolling into cylindrical shapes on plate bending machines. In the weld bays, the longitudinal seams of each cylinder, called cans, are joined using submerged arc welding. These cans are then either built into larger tower sections or transferred to the flange table, where precision machine flanges are installed and welded. Section build-out completes the structural form of each tower segment. After structural welding, sections move to finishing halls for blasting, glass cleaning, and protective coating. Internal components such as platforms, cabling conduits, and down-tower wiring systems are installed before final inspection. Submerged arc welding is supported by advanced Lincoln Electric AC/DC 1000 systems with tandem wire manipulators ensuring consistency and penetration. Once assembled, coated, and outfitted, each section is tarped, staged, and prepared for shipment. This process delivers reliable wind tower components, engineered for strength and long-term performance in renewable energy infrastructure. Witness the installation of a next-generation GE wind turbine at the wind test site in Vang, the Netherlands, a project that demonstrates both engineering precision and the scale of modern renewable energy technology. The process begins with the assembly of the tubular steel tower, designed for stability and strength, reaching an impressive hub height of 131 meters. Each tower section is carefully lifted and aligned using heavy lift cranes, ensuring structural accuracy to withstand years of operational stress from wind forces. Beside the tower, the massive rotor components are prepared. Each blade, measuring 67.2 meters in length, is positioned for final assembly. Once mounted, the blades form a rotor diameter of 137 meters, capable of sweeping an enormous area to capture wind energy efficiently. The installation requires precise coordination, as cranes lift the rotor hub and blades into place, where technicians secure them at elevation with millimeter accuracy. The upgraded generator, rated at 3.6 megawatts, integrates with the rotor system to maximize energy conversion. Combined with the increased rotor size, this design significantly boosts annual energy production compared to older turbine models. The new configuration not only delivers more electricity per unit, but also ensures reliable performance in varying wind conditions, making it an ideal solution for expanding renewable energy capacity. Once the nacelle, hub, and blades are secured, commissioning teams connect electrical systems and perform diagnostic checks to validate alignment, rotation, and power output. The completed turbine stands as a towering example of advanced wind technology, capable of generating enough clean energy to supply thousands of households. This installation reflects the ongoing evolution of wind power: larger, more efficient machines that capture more energy with fewer units, setting a new standard for sustainable electricity generation. The HAWART system for wind turbine blade assembly is designed to ensure precision, safety, and efficiency during the critical joining stage. The process begins with the locking mechanism, securing the blade in position before controlled movement is initiated. In the first opening step, the mold gradually adjusts to release stress and prepare for alignment. The second opening step follows, supported by two robust rotating axles that guide the blade into the correct orientation with an exact swivel angle of 55.8 degrees. Each hydraulic cylinder plays a vital role, enabling the upper mold to swivel approximately 90 degrees to 180 degrees, allowing seamless adjustment between blade and hub. This controlled rotation ensures that tolerances are maintained, minimizing stress concentrations and guaranteeing aerodynamic accuracy. By combining synchronized locking, axial rotation, and hydraulic swiveling, the HAWART system delivers a reliable, repeatable method for blade assembly, essential for maximizing turbine efficiency and long-term wind energy performance. The Borwind 3 jacket installation marked a key step in Germany's offshore grid expansion. Located about 130 kilometers off the coast in 40 meters of water, the six-legged jacket foundation was fabricated by Hydropower Fabrication Group and weighed approximately 5,600 tons, with an additional 4,800 tons of skirt piles. In May 2018, Hydropower marine contractors transported the structure offshore using heavy-lift vessels and carefully lowered it into position on the seabed. The piles were then driven deep into the ground to secure the jacket, ensuring long-term stability against harsh North Sea conditions. Built for Tenetti's 900 megawatts Borwind 3 HVDC platform, the jacket serves as the supporting base for the Siemens manufactured topside, which will convert alternating current from offshore wind farms into direct current. This installation is a crucial milestone, enabling clean wind energy to be reliably transmitted into Germany's national power grid. The Ichthys LNG project gas export pipeline represents one of the most complex subsea installations ever undertaken in Australian waters. Saipem was responsible for engineering and execution, including shore approach works at Darwin, preparation inside Darwin Harbour, and the offshore laying of the concrete-coated pipeline extending toward the Ichthys field. Central to the project was the deployment of the Castorone, a state-of-the-art pipelay vessel operating in Australian waters for the first time. This was also the vessel's first assignment involving a concrete-coated pipeline and its first installation in shallow water conditions. The operation began in depths of around 60 meters and advanced to 250 meters at the final offshore section. Pipeline construction required sequential processes. Pipe joints were cut, aligned, and welded into triple joint segments. These were then inspected and subjected to non-destructive testing to ensure integrity before being coated and lowered onto the seabed. Castorone achieved a record output during this project, 122 triple joints, equal to more than 4.5 kilometers of pipeline in a single day. Engineering teams also had to account for strict Australian environmental and safety regulations. Special protection measures were integrated for the harbour section to safeguard marine ecosystems while maintaining structural reliability. The project's complexity extended beyond welding and laying operations. Logistics were coordinated at the scale of a small town, involving continuous flow of materials, specialized equipment, and skilled personnel. From pipe delivery to offshore deployment, every stage required synchronization to maintain productivity and minimize downtime. By combining advanced vessel technology, precision welding systems, and rigorous quality control, the Ichthys LNG pipeline installation was completed to the highest standards. Each stage, from shore preparation to subsea laying, demonstrated the technical discipline required to deliver one of the world's longest subsea pipelines. Have you ever wondered how the invisible lifeline of an offshore wind farm actually reaches the shore? At Galloper, this process begins with nearly 50 kilometers of heavy subsea cable, carefully loaded and tested before leaving port. The Galloper offshore wind farm cable shore landing demonstrates the precision and coordination required to connect offshore renewable energy to the onshore grid. The 24-hour operation began at Fela North, where approximately 47 to 48 kilometers of subsea export cable were carefully loaded into the vessel's carousel. Each layer was laid with precision to avoid mechanical stress, ensuring smooth deployment during installation. Before departure, the cable underwent rigorous testing. Optical fibers were checked with optical time domain reflectometer systems for data transmission reliability, while aluminum conductors were verified with time domain reflectometry to confirm electrical integrity. Only after certification did the vessel depart, navigating through the niche channel and IMU locks before setting course for the southeast coast of the United Kingdom. At the landfall site near Sizewell, stability was critical. A pre-arranged anchor spread of 7 anchors was deployed with the support of 2 anchor-handling tugs, securing the vessel in position. A survey team, consisting of 4 specialists, coordinated both surface and subsea positioning using GPS and acoustic systems, aligning the vessel and subsea equipment with precise project coordinates. The heart of the installation relied on the subsea plow. The export cable entered through a front bellmouth, where load cells continuously monitored tension. Hydraulically operated skids adjusted trenching depth between 5 and 10 centimeters, enabling the plow to adapt to seabed conditions. As the plow advanced, twin tow bridles provided pulling force, while the cable was guided over horizontal tines before exiting through the depressor. This controlled placement ensured the cable rested securely on the seabed, with constant feedback to the control van for real-time adjustments. The shore landing sequence demanded careful timing with tidal conditions. A messenger wire was pulled from the beach to the vessel, allowing the cable to be drawn ashore during slack water. Buoyant floats supported the cable across the surf zone, preventing damage. To maintain safety and avoid diver intervention, a sea serpent flotation system was used. Once positioned, it was deflated, lowering the cable gently onto the seabed. With the landing complete, burial operations began along the 43-kilometer export route. The plow embedded the cable to a protective depth, shielding it from anchors, fishing activity, and seabed movement. Precise layback monitoring maintained correct tension and alignment, ensuring consistency along the corridor. This shore landing represented the opening phase of a broader campaign to connect the Galloper offshore wind farm to the grid. Through a combination of heavy marine engineering, subsea technology, and strict safety protocols, the project ensured a secure and durable pathway for transmitting clean offshore energy to households across the region. Hopeful. The maintenance and overhaul of a steam turbine follow a structured sequence of inspections and machining operations to restore performance and ensure safe operation. The process begins with rotor balancing, where any mass imbalance is corrected to prevent excessive vibration. This is followed by fluorescent penetrant inspection, FPI, used to detect fine surface cracks that cannot be seen by the naked eye. The rotor then undergoes precision machining, while ultrasonic testing is applied to identify subsurface flaws within the material. For the turbine casings, a full dimensional analysis is performed, and boring operations are carried out to restore alignment and tolerances. Dynamic verification takes place in the high-speed balance bunker, using spare bearings and oil seals to replicate actual running conditions. In cases where original drawings are unavailable, reverse engineering is employed to recreate components to exact specifications. Surface recovery often requires submerged arc welding, followed by post-weld heat treatment to relieve residual stresses and restore metallurgical stability. Throughout the entire workflow, strict quality control procedures are applied, including dimensional checks, tolerance verification, and metallurgical analysis. These combined measures ensure that the turbine components meet durability requirements and can return to service with reliable efficiency and extended operational life. Ceramic matrix composites, CMCs, are structural ceramics reinforced with continuous ceramic fibers, most commonly silicon carbide (SiC) fibers, embedded in a SiC matrix. The critical element that enables toughness is the interphase coating applied to each fiber, commonly pyrolytic carbon or BN-type layers, often proprietary. That compliant interface promotes crack deflection and fiber pullout, giving CMCs metal-like damage tolerance while retaining ceramic heat resistance. CMC component production follows several technical stages. It begins with fiber manufacture, high-purity SiC fibers produced to tight diameters and tensile specifications. Fibers are processed into textile preforms, weave, braid, or unidirectional tape shaped to the component geometry. The preform is then densified by one of several matrix infiltration routes: chemical vapor infiltration (CVI), polymer infiltration and pyrolysis (PIP), or melt infiltration to consolidate a continuous SiC matrix around the fibers. Each route balances production rate, achievable density, and residual porosity. CVI gives high-quality microstructure but is slow, while PIP can be faster but may require multiple cycles. After densification, components undergo precision machining with diamond tooling and receive environmental barrier coatings (EBCs) to protect against oxidation and corrosive species at extreme temperatures. Joining and integration to metallic structures requires specially designed interfaces and seals to accommodate differences in thermal expansion and stiffness. Quality assurance relies on NDE methods, ultrasonic inspection, X-ray CT scanning, and microstructural sampling to verify porosity, fiber alignment, and interface integrity. Scaling CMCs from prototypes to thousands of parts demanded supply chain and manufacturing transformations. Key steps include scaling fiber production, NGS advanced fibers expanded capacity, automated tape and preform layup, controlled furnaces for densification, and automated inspection systems. GE's strategy layers research labs and lean manufacturing, small-scale prototyping and R&D, process maturation in lean labs, then transfer to automated mass production lines, e.g., Asheville facility, with traceable process control. Performance advantages are direct and quantifiable. CMCs have roughly one-third the density of superalloys and tolerate several hundred degrees Celsius higher service temperatures. This reduces cooling air requirements and enables higher cycle temperatures, translating into improved thermal efficiency, higher thrust, and measurable fuel burn reductions. Manufacturing challenges remain: consistent interface quality, controlling residual porosity, machining yield, and qualification across many flight hours, but ongoing process automation, fiber supply scaling, and rigorous test programs are addressing these barriers. In sum, the GE CMC program is a systems-level engineering effort. Material science, textile preform engineering, infiltration chemistry, coating technology, precision machining, and production-scale automation all converge to deliver high-temperature, lightweight components for next-generation turbine cores. Hulkend. The production of roll-forming lines at the Lipetsk plant of roll-forming equipment demonstrates the scale and precision of modern metalworking. Products such as profiled sheeting and metal tiles are essential to construction across the country, with factories processing thousands of tons of rolled steel every day. To meet this demand, since 2004, the Lipetsk plant has been designing and manufacturing roll-forming mills for flat-sheet steel. The principle of forming a profiled sheet is straightforward. A smooth steel sheet passes sequentially through stands of the roll-forming mill, each set of rollers gradually reshaping it. For metal tiles, additional stamping units create transverse steps at defined intervals before the finished product is cut to length. The manufacturing process of the equipment itself begins with raw stock preparation. Long steel sections are cut into blanks that will later become components of the roll-forming line. These blanks move to machining centers, where precision work is carried out. Shafts for the mill, which hold the profiling rollers, are turned on high-accuracy lathes. In parallel, other components are produced: bearing housings, supports, clamps, and frames, numbering in the thousands for a single machine. Profiling rollers are manufactured on CNC machining centers, ensuring exact geometry. Next, frame assemblies for the mill are welded together and sent for painting. Another essential mechanism, the decoiler, is prepared in parallel. This device unrolls the steel coil and feeds it into the mill, with automated tension control linked to the feed speed. After painting and installation of the control panel, the decoiler is ready for operation. Assembly of the mill follows strict engineering documentation. Each roller is keyed to its shaft and secured with nuts on both sides. When the frames are painted and dry, uprights are mounted to hold the roll stands. Lower shafts are installed first. Then upper shafts are positioned and temporarily fixed. Precise adjustments of the gaps between rollers come later, after another painting stage. Every machine produced at the Lipetsk plant follows this precise sequence, combining mechanical engineering, precision machining, and automation. The result is robust roll-forming lines capable of producing the profiled sheets and metal tiles that shape modern construction. A critical part of the line is the guillotine shear. This unit cuts finished profiles into sheets of required length. The blades for these shears are also precision machined. Even the slightest deviation from the product's geometry would produce poor cuts. To extend service life, blades are heat-treated, heated to high temperature, then quenched in water or oil. Once blades, shafts, and structural components are installed, the line is wired with drives, terminals, and control systems. Chains are mounted to synchronize the rotation of all shafts. Final alignment ensures coaxial positioning of rollers and the correct gap between upper and lower shafts. When fully assembled, the line operates as an integrated system. The decoiler unwinds the coil, the roll-forming stands shape the profile, the guillotine shear cuts it, and the automation system coordinates the process. The construction of built-up H-beams is a carefully controlled industrial process that combines advanced design software, precision fabrication, and rigorous quality checks. The workflow begins with shop drawing preparation using Tekla software, which provides detailed specifications for each beam. Based on these drawings, the nesting process optimizes material usage before production begins. Incoming steel plates undergo inspection for quality and dimensional accuracy, followed by the cutting process, where automated systems prepare the components. These plates are then moved into the assembly stage, where they are aligned and tacked into position, ready for joining. Welding is performed through the submerged arc welding process, producing deep, uniform welds with minimal defects. Post-weld, the beams are subjected to straightening operations to eliminate distortions. To ensure reliability, multiple inspections are carried out, including dimensional checks, visual testing, tolerance verification, and non-destructive testing, NDT. Once approved, beams pass to the fitting stage, where qualified fitters and welders complete final adjustments and connections. Surface preparation follows with automatic shot blasting, removing rust and impurities to achieve the required roughness profile. Afterward, the beams enter the painting and coating stage, where thickness is measured for consistency. The process concludes with final inspections, ensuring every built-up H-beam meets structural and safety standards before being dispatched as finished goods ready for delivery and installation. How a simple steel wire transforms into the robust cables that power cable cars and lift systems. In just 2 minutes at the Verkeershaus exhibition, the process unfolds with clarity and precision. First, steel wire rods are fed into drawing machines, where each strand is finely stretched and reduced in diameter, built for strength and flexibility. These multiple drawn wires are then carefully aligned and assembled into strands, which are helically wound around a central core to form a solid, flexible rope. The formation continues as strands are compacted and shaped through a closing process, maintaining uniform layering. Quality control is constant, checking strand tension, wire diameter, and geometric integrity. Finally, the complete cable is reeled, tested, and prepared for real-world application. This seamless sequence, from wire drawing, strand formation, and cable closing, highlights the craftsmanship behind every durable cable that transports people and goods. At the heart of the exhibit, you can witness how raw metal gains structure, strength, and purpose, ready to take on the Alps. KTL Offshore Private Limited operates one of the world's most advanced rigging facilities, with the capability to manufacture heavy-lift wire rope slings up to 24 inches in diameter. The fabrication process of an 18-inch Flemish I-sling begins with a team briefing on quality control protocols, ensuring compliance with engineering-approved procedures. Steel wire ropes are first verified against mill certificates before being cut to length on precision spool machines. To form the initial Flemish I, the rope end is manually separated, the steel ferrule inserted, and dimensions checked with a T-bar gauge. The assembly is then transferred outdoors for swaging, where the ferrule is compressed in multiple stages using calibrated molds. After each swage, dimensional accuracy is rechecked to maintain tight tolerances. For the second Flemish I, lay length is marked according to quality standards, ropes are twisted, aligned, and inspected for correct body length before swaging. Component ropes are positioned side by side, secured with brackets, and reinforced with fireproof blankets and welded clamps for safety. The completed sling undergoes final weaving, labeling, and preparation for load testing. All testing is witnessed by an ABS-certified inspector, ensuring conformance to international standards. Throughout the process, strict health and safety measures are applied, safeguarding personnel working in proximity to heavy mobile equipment. The Alcoa smelting process begins in the green mill, where carbon anodes are manufactured from petroleum and metallurgical byproducts. Each anode, weighing around 900 pounds, is baked in a ring furnace at 2000 degrees Fahrenheit for up to 6 days. In the smelter, each pot operates with 26 anodes, which have a 20-day service life. With 150 pots per room and 5 pot lines in operation, the scale is immense. Alumina, shipped from countries such as Australia or Brazil, is conveyed into the pots, mixed with molten cryolite and exposed to 130,000 amps of electrical current. This electrochemical process separates aluminum from oxygen, producing more than 300,000 pounds of aluminum per pot line each day. The molten metal is tapped, impurities removed, and then cast into ingots for further use. The extrusion of PVC window profiles represents a highly controlled, continuous manufacturing process designed for precision and durability. It begins with the feeding of raw PVC compound into the extruder, where the material is plastified under carefully regulated temperature and pressure. As the molten PVC exits through a specialized die, the distinct geometry of the window profile begins to take form. Immediately upon exiting the die, the profile passes through a calibration unit. This station is equipped with vacuum technology that stabilizes dimensions and ensures tight tolerances. Water cooling channels within the calibrator extract heat rapidly, fixing the profile shape while maintaining consistent structural integrity. Following this stage, the profile enters a multi-stage cooling bath, where circulation-controlled water further solidifies the PVC, preventing warping and deformation. Next, the extrusion line incorporates a haul-off or pulling unit, which applies synchronized traction to guide the continuous profile steadily through the downstream equipment. This precise pulling action guarantees that the surface finish remains smooth and free from defects. Through this combination of extrusion, calibration, cooling, haul-off, and cutting, the process ensures PVC profiles that meet rigorous industry standards for dimensional accuracy, weather resistance, and long-term performance. The process concludes with cutting and packaging operations. Automated saws cut the cooled PVC profile to exact lengths specified for window frame assembly, while downstream handling equipment organizes and stacks the finished profiles for delivery. At Wanapum Dam, engineers completed the final placement of the 10th turbine runner, head cover, and shaft assembly, marking the conclusion of a project that began in 2004. The new turbines, rated at 150,000 horsepower, replace older 120,000 horsepower units, delivering both higher output and efficiency gains of up to 5%. Precision inspections ensured components from suppliers worldwide fit seamlessly. Pre-assembly methods reduced installation time, while fish-friendly designs now combine efficiency with environmental responsibility. Have you ever wondered how those massive, four-legged concrete structures that line coastlines, called tetrapods, are actually made? The process begins with the assembly of the formwork, arranged step by step with end plates and scaffolding, lifted and aligned into position using a crawler crane. Large sections of the formwork are joined with tapered pins, cotter pins, and wedges before the structure is fully secured. Once completed, release agents are applied to the inner surfaces to prevent adhesion of fresh concrete. Concrete arrives in agitator trucks, then is transferred to the red pumping vehicle, which delivers the mix directly into the mold. In rainy conditions, protective frame-mounted covers prevent rainwater contamination. Before pouring, on-site tests are conducted, including slump, air content, temperature, and unit water measurement. Sample test pieces are also cast for later compressive strength verification. Placement is carried out in 4 successive layers. Each layer is compacted using vibrators, removing entrapped air and ensuring density, with operators stationed at each leg of the tetrapod. Safety harnesses are mandatory during these elevated operations. As the upper layers are poured, vibrators continue to remove air bubbles. Near completion, nozzle residues are carefully removed, and finishing is performed with a Picacon device, reducing surface voids. A curing compound is then sprayed over the exposed surface, followed by temporary covers to prevent rapid moisture loss. After sufficient curing, the formwork is dismantled with a crawler crane. Each formwork panel is brushed clean for reuse in the next cycle. The newly demolded tetrapod undergoes membrane curing, where liquid agents form a protective film, reducing evaporation and enhancing strength development. After several days, water testing confirms the surface integrity. The result is a fully completed tetrapod, ready for coastal installation, where it will serve as a durable structure against wave energy. The construction of an Archimedes screw hydro turbine at Riverdar Country Park marked a shift toward efficiency and reliability in small-scale hydropower. Installed in 2006 and commissioned in January 2007, the project replaced an aging Kaplan turbine that had become difficult to maintain. Civil works began with channel preparation and reinforced concrete foundations, designed to anchor the screw and control water flow. The turbine itself, a steel helix mounted on bearings, was assembled on site and aligned precisely within its trough to ensure smooth rotation. Water from the river drives the screw, transferring energy to a gearbox and generator housed in a protective enclosure. With minimal moving parts and low rotational speed, the Archimedes screw offers durability, high efficiency across variable flows, and reduced environmental impact, securing reliable renewable power for the park. Hydropower. The semi-automatic armature winding machine is designed for the efficient production of small and medium-sized electric motor components. It utilizes a double flyer winding system which enables precise and consistent wire placement on the armature slots. This configuration ensures balanced coil distribution and improves the electrical and mechanical performance of the final motor. The machine is compatible with various motor types, including mixer motors, DC motors, vacuum cleaner motors, and power tool motors. Its semi-automatic operation makes it especially suitable for manufacturers with moderate production volumes, offering a balance between manual flexibility and automated accuracy. During operation, the operator sets up the wire specifications and winding parameters through a control interface. The armature is then positioned, and the double flyers rotate simultaneously to guide the enameled copper wire into the slots with controlled tension. After each layer is wound, the machine indexes the armature to the next slot, ensuring uniform coil formation. The system includes a tension control mechanism, wire guiding system, and programmable slot positioning to maintain precision. Once winding is completed, coil ends are automatically arranged for the next process, such as forming, lacing, or welding. By integrating automation with manual oversight, the semi-automatic winding machine provides accuracy, repeatability, and efficiency, while remaining versatile for different motor applications.